Welcome back to the channel. Today, we're diving into one of the most important results in mathematics, the Fundamental Theorem of Arithmetic. This theorem tells us something profound. Every whole number greater than 1 can be uniquely broken down into prime numbers. Think of primes as the atoms of arithmetic, the building blocks of all integers. Before I state the theorem, let's recall what a prime number is. A prime is a natural number greater than 1 that has exactly two positive divisors, 1 and itself. For example, 2 is prime because its only divisors are 1 and 2. The same holds for 3, 5, 7, and so on. And if we look further, we find there are infinitely many primes. A formal representation of the set of prime numbers is the following. Note that the set of prime numbers is a subset of the natural numbers, and each prime has exactly two divisors, 1 and itself. One important detail, the number 1 is not prime since it has only one positive divisor. That makes 2 the first prime number, the smallest one, and the only even prime. Now let's state the theorem. Every integer greater than 1 is either prime itself, or can be written uniquely as a product of prime numbers. This is the mathematical notation that represents the theorem. We can see the product of those primes and the exponents alpha, more explicitly written as follows. As I said before, the primes must be greater than 1. The only rule for the exponents alpha is that they must be natural numbers. To make this clearer, consider the number 1200. Remember that the set of prime numbers begins with 2, 3, 5, and 7. The idea is to divide 1200 by these primes, find which of them are divisors of 1200, and take the product of those primes raised to the appropriate powers. Let's see that in practice. Note that we may divide 1200 by the same prime more than once. The exponent indicates how many times we can divide 1200 by that prime. For example, 2 divides 1200 4 times, 3 divides it once, and 5 divides it twice. One important thing is that it doesn't matter in what order you do the division. The result will be always the same. Another important thing is that the representation of a number as a product of primes is unique. You can change the order of the division, but the final number is the same. You can see this during the proof of the theorem. I won't present the proof here because I want to focus on useful applications rather than the proof itself. But you must consider that statements as mathematical truths. Now let's examine what we can do with this theorem. The first application is finding the greatest common divisor, GCD. This means to find the largest integer that divides every number in a chosen set. For example, what is the greatest common divisor of 360 and 840? One tedious approach is repeated division. Depending on the size of the number, it appears a lot of divisors, and this method takes too much time. A far simpler method uses prime factorization. To do that, express both numbers as products of primes, and select the primes they have in common with the smallest exponents, and multiply those primes together. The result is the GCD. The first method works well for small numbers such as 8 and 4. For large numbers like 1200 and 3400, a better approach is the Fundamental Theorem of Arithmetic. You should consider which method is most appropriate. The second application is finding the least common multiple, LCM. What that means? It is the smallest positive integer that is a multiple of each number. Again, considering 360 and 840, you could list multiples, which is inefficient. Instead, factor each number into primes and take the largest exponent of each prime. After that, multiply those primes. That yields the least common multiple of those numbers. Those are some immediate uses. But the theorem's influence extends much further. For example, the classical proof that square root of 2 is irrational relies on unique prime factorization. The theorem also underpins the study of factorials and the derivation of Euler's totient function. Like any mathematical result, the fundamental theorem of arithmetic depends on its assumptions. In more advanced settings, such as certain rings studied in algebraic number theory, unique factorization can fail. Mathematicians therefore developed concepts like unique factorization domains to handle those cases. In short, the fundamental theorem of arithmetic guarantees that primes are the indivisible building blocks of the integers. Without it, much of our work on divisibility, modular arithmetic, and even modern cryptography would be far less secure. Next time you see a large number, remember, it's just a collection of primes hiding inside. If you enjoyed this breakdown, hit like, subscribe for more deep dives, and thank you for watching. God bless.